Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video I'm going to explain why an argument in Stephen French's review of our book is fallacious. This is the book in question. As you can see, it was blurred by some prominent researchers in the field. Here's where you can find the entire review. I'm only going to respond to the fallacy. Okay, here's what French wrote. To compare quantum entanglement with length contraction and special relativity, he writes, the authors would have to regard their invariant quantity, based on the qubit, as an element of an independent reality, just like the space-time interval. However, such a realist view of quantum information has long been comprehensively demolished by Timson. The obvious alternative, then, is to take the qubit as reflecting our knowledge about a system and adopt the view attributed to Bohr as cited by SSM themselves. There is no quantum world. At this point, however, those working in the foundations of physics, philosophers and physicists alike, will no doubt cry out as one, "Been there, done that." The history of the field is littered with such retreats from the attempt to understand quantum mechanics in terms of what it says about how the world is. So here's French's argument, premise, conclusion form. Premise 1. The space-time interval is the objective and invariant quantity that does the explanatory work in special relativity. Premise 2. The equivalent of the space-time interval for the authors is the qubit. Premise 3. This leads to a dilemma for Stuckey, Silberstein, and McDevitt. Either quantum information is alleged to be objective, like the space-time interval, realism about quantum information, or the qubit just represents knowledge about the quantum system in question, anti-realism. Premise 4. Everyone knows realism about quantum information is ridiculous and false. Premise 5. If Stuckey, Silberstein, and McDevitt's view entails anti-realism about quantum mechanics, then, just as Bohr accepted, it tells us nothing about the nature of reality. Conclusion. Given premises 4 and 5, the authors can't possibly explain quantum superposition, complementarity, and entanglement. Premise 3 of French's argument is false, because it presents a false dilemma. Our account no more entails fundamentalism about quantum information than the concept of a classical bit entails the simulation hypothesis. When we refer to a qubit, we are talking about the physical instantiation of a bit of quantum information. Just like a classical bit, a qubit can be multiply instantiated in different physical systems. In our book, we explain the spin 1/2 qubit, the photon polarization qubit, and the double slit qubit. Obviously, these are all referring to some real phenomena in spacetime. We make this point explicitly on page 167, as this photo shows. This is the page immediately opposite the page with Peterson's quote about Bohr's belief, quote, "there is no quantum world," that French quotes in his review. So we're not sure why French didn't see this or doesn't understand it. While his argument fails on that point, the origin of his fallacy is far more interesting, and it resides in premises 1 and 2. Let me explain. As I explained in previous episodes of Einstein's entanglement, physicists, including Einstein, were trying to find a constructive explanation for the observer independence of the speed of light c, whence the Lorentz transformations. That is, they were looking for some causal mechanism, like the luminiferous ether, to explain length contraction, which would account for the null result of the Michelson-Morley experiment. That is, everyone measures the same value for c, regardless of their relative motions. But after years of failed attempts, Einstein writes, "By and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results." That is, he abandoned a causal explanation for the light postulate, constructive efforts, and instead said it had to be true, as pointed out here by John Norton in his course on special relativity. Thus we see that special relativity is what Einstein called a principle theory, which means its kinematics follows from an experimentally motivated postulate, the observer independence of c. And that postulate must be true if the relativity principle and Maxwell's equations are true. In this respect, special relativity provides a principle explanation. This is so widely accepted that it appears in introductory physics textbooks without qualification or controversy. Today, we still have no consensus causal/constructive counterpart to special relativity, and physicists long ago gave up looking for one. So we have Einstein's principal solution to the mystery of length contraction as follows. The relativity principle and Maxwell's equations demand the observer independence of C, whence the Lorentz transformations containing length contraction. This principal explanation of length contraction from special relativity is what we replicate for quantum entanglement in our book, as I've shown in previous episodes of Einstein's entanglement. But not everyone thinks that length contraction follows ultimately from the relativity principle. Some believe special relativity provides structural explanation, whereby the Minkowski spacetime formalism itself provides the most fundamental explanation. In French's case, as indicated by his premise 1, length contraction follows ultimately from the invariant spacetime interval. So, with respect to special relativity, we simply disagree as to which is the more fundamental explanans, the invariant spacetime interval or the relativity principle. But let me show you how this difference between principal and structural explanation manifests itself for quantum entanglement, where it will be clear which is the more fundamental explanans. French is correct in assuming that the invariant structural element from quantum information theory for explaining quantum entanglement is the qubit. In our book and published papers, we start with Bruckner and Zeilinger's principle of information invariance and continuity from the axiomatic reconstruction of quantum mechanics via information theoretic principles, also known as the quantum reconstruction program. Don't worry about the fancy language. I'll make everything conceptually clear in what follows. So information invariance and continuity simply states the total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. As we shall see, this is just an information theoretic way to describe qubit superposition. So this is the experimentally motivated postulate, whence the Hilbert space formalism of quantum mechanics. Just like the light postulate is the experimentally motivated postulate, whence the Minkowski space formalism of special relativity. Now let me explain what all this means using spin 1/2 qubits. I will use electron spin as the example of the spin 1/2 qubit. As Stern and Gerlach sent silver atoms through a non-uniform magnetic field, they found the atoms were deflected up towards the north magnetic pole or down towards the south magnetic pole, never anywhere in between. The deflection was eventually attributed to the spin angular momentum of the silver atom's valence electron, which equals plus or minus Planck's constant h from Planck's radiation law divided by 4 pi. This is our spin 1/2 qubit in the state psi equals z plus. We then measure our qubit in the b hat direction, making an angle theta with z hat, as shown here. The outcome of such a measurement is described by Dirichlet's discreteness with continuity requirement. There is a continuous infinity of possible measurements of a spin, as there are infinitely many directions of space in which an angular momentum can be measured. In contrast, there are only 2 possible outcomes for each of these measurements, plus or minus h bar over 2. H bar is just h divided by 2 pi. If the system is found to have the momentum plus h bar over 2 in a given direction, a subsequent measurement performed in a direction making an angle theta with the former direction, like I had with b hat and z hat there in the previous slide, will give either plus or minus h bar over 2. Now this is not at all what we expect from simple Newtonian mechanics, since spin is a form of angular momentum. We expect to obtain the projection of plus 1 z hat in the b hat direction, or plus 1 cosine theta. So Dirichlet adds his correspondence requirement. The average angular momentum in the direction theta must be equal to the projection of the initial angular momentum in this direction. This is so by a correspondence argument. Then you get this average-only projection shown by the equation there, and you solve that with your normalization, meaning the sum of the probabilities has to always be 1, and you obtain your qubit probabilities, quantum mechanics. Now let me use Dirichlet's intuitive derivation of our qubit probabilities to explain Bruckner and Zeilinger's experimentally motivated postulate of information invariance and continuity. So the information contained in our spin 1/2 qubit, psi equals z plus, right, is that a z hat spin measurement of psi will produce plus 1 with an outcome of 100%. I mean, that's the state we're in. And we measure it there, that's what we get. That's what it means to be in that state, right? Now this information gets spread out between plus 1 and minus 1 outcomes as our SG measurement direction, b hat, continuously changes its angle theta with respect to z hat. Then the distribution over those plus 1 and minus 1 outcomes always totals 100%. So this corresponds to the total information of one bit is invariant under a continuous change in measurement direction b hat. Okay, now the maximum randomization of our initial qubit of information, plus one outcome with 100% probability in the z-hat direction, occurs for the so-called complementary measurements. That's when theta equals 90 degrees. Then your probabilities for plus one and minus one are 50% each, totally random. Now, when you have b hat is x hat and b hat is y hat, then those become the 90-degree directions for the z hat. And that gives you a basis, right, of mutually complementary spin measurements. Then b hat itself would have such a basis. The picture shows there on the left, a figure. And so we have the second half of information invariance and continuity between different complete sets of mutually complementary measurements. Information invariance and continuity is qubit superposition. Now, to obtain the joint probabilities for a Bell spin state, Dergel simply adds conservation requirement to his discreteness with continuity and correspondence requirements. We do the same. I'll skip that explanation in this video. You can see it in a few of the videos I have in Einstein's Entanglement playlist. We don't need that to reveal French's fallacy. Here's what Dergel says about the fundamental requirement of discreteness, revealing French's fallacy. From a physical point of view, discreteness is a non-trivial assumption. In the present state of this approach, we should probably content ourselves with the insight that quantum discontinuity, if it is admitted as a fundamental feature of the microworld and complemented with natural axioms concerning the relationship between the micro and the macroworld, necessarily leads to quantum mechanics as we know it. In other words, he is saying that we have no justification for the discreteness, whence qubit superposition, other than it gives the Hilbert space of quantum mechanics. Thus, the derivation of the Hilbert space formalism of quantum mechanics from discreteness with continuity and correspondence is exactly like deriving the Lorentz transformations from the light postulate without bothering to justify the light postulate with the relativity principle in Maxwell's equations. This is structural explanation for quantum mechanics based on the invariant qubit as called for in French's argument. You can see why it hasn't garnered consensus support in the quantum foundation community, right? Van Kamp writes, nothing additional has been shown to be incorporated into an information theoretic reformulation of quantum mechanics beyond what is contained in quantum mechanics itself. So it's not offering any explanatory value on that front. And this is what Lorentz had to say about Einstein's reconstruction of his Lorentz transformations. Einstein simply postulates what we have deduced with some difficulty and not altogether satisfactorily from the fundamental equations of the electromagnetic field. In other words, Einstein said, well, I'm going to start with this fact. Everybody measures the same value for the speed of light c, regardless of their relative motions. And Lorentz says, what? You can't start with, that's the mystery. That's why we introduced the luminiferous ether and link contraction to begin with, right? But note, he says, by doing so, he may certainly take credit for making us see in the negative result of experiments like those of Michelson, Rayleigh, and Bryce, not a fortuitous compensation of opposing effects, but the manifestation of a general and fundamental principle. In other words, without the general and fundamental principle of relativity, no one would have accepted Einstein's reconstruction either. So let me show you how Dergel's discreteness with continuity requirement, fundamental to qubit superposition, that is information invariance and continuity, follows from the relativity principle, thus proving that the relativity principle is a more fundamental explanans for quantum entanglement than the invariant qubit. Again, start with the Stern-Gerlach measurement of spin. Dergel writes, there is a continuous infinity of possible measurements of a spin, as there are infinitely many directions of space in which an angular momentum can be measured. In contrast, there are only two possible outcomes for each of these measurements, plus h bar over 2 or minus h bar over 2. Thus, as Steven Weinberg pointed out, when you measure electron spin with Stern-Gerlach magnets, you're measuring Planck's constant h. And what's true about such measurements is that the electrons are always deflected the same amount up or down relative to the north-south magnetic poles for a particular source, no matter which way the Stern-Gerlach magnets are aligned in space. Now let me summarize everything I just said. Everyone measures the same value for Planck's constant h, regardless of how they are oriented in space. Looks a lot like the light postulate, right? Indeed, inertial reference frames are related by spatial rotations as well as boosts, and Planck's constant h comes from the Planck's radiation law, just like the speed of light comes from Maxwell's equations. So the relativity principle justifies discreteness with continuity, characterizing the fundamental invariant structural element of quantum mechanics, the invariant qubit. Consequently, Knight could mirror his principal introduction to special relativity for a principal introduction to quantum mechanics. In conclusion, French's proposed structural explanation of quantum entanglement by the invariant qubit is not as fundamental as our principal explanation of quantum entanglement via the relativity principle. French's fallacy is to believe the qubit, as the objective and invariant quantity of quantum mechanics, does the explanatory work in quantum mechanics. In fact, the invariant qubit contains the mystery of quantum superposition that needs to be resolved itself before it can be used to resolve the mystery of quantum entanglement, and the relativity principle does just that. Sorry, Stephen. Principal explanation clearly trumps your structural explanation for quantum mechanics.